My name is Ivar. I'm one of the TAs at the Transport Phenomena course you're taking right now. And in this video, I'm going to solve the exercise given in week 4, subsection 1, namely the electrical wire exercise. In this exercise, we are given some parameters like the lambda, which is 400 watts per meter Kelvin, the diameter of the wire, which is 25 centimeters, also known as 0.25 meters, a heat production in the wire of 20 watts, the length of the wire is 200 meters, and both ends are cooled and kept at a constant temperature of 273.15 kelvins. Now, to also place them within the figure, the temperatures are kind of easy. They are just at the edges of the wire, the diameter figures. The lambda and the Q are both properties of the wire itself, and the length of the wire is shown like this. The problem is symmetrical in nature, with each of the half lengths of the wire representing a full temperature profile, with the highest temperature achieved at the middle of the wire. We'll call it T center or TC, and so half of this wire also has the same diameter D, the same lambda, and only half of the heat production. For convenience, we'll denote the middle of the wire as X is 0. And the first question asked in this electrical wire exercise 4.1.13 is to assess the area perpendicular to the heat flow through which the heat will flow in meters squared. The area perpendicular to the heat flow is just a cross-sectional area of the wire, since the wire has been perfectly insulated all around. And this is just pi r squared, or P times the diameter squared over 4. And if we then fill in the data we've been given, we'll end up with 0.0491 meters squared. For the next question, which is 4.1.14, the question is, how large is the heat flow through the wire in terms of the heat production? Solve this by setting up an energy balance. So, first up is to construct the energy balance. The problem is in steady state, so we can construct a steady state thermal energy balance, which reads the change in time, which is 0, equals in, well, the inflow is 0, minus out, VQ is what's flowing out, plus Q over 2. And then to put the heat flow in terms of the heat production, we just have to solve for VQ in terms of Q, and we can even fill in the number, which is 10 watts. Then, the last question for this exercise is to derive an expression for the temperature in the wire over the distance in the cable by using Fourier's law, and then to calculate the temperature in exactly the middle of the wire. First up is the Fourier's law, which reads as the heat flux is equal to minus the heat conductivity times the derivative of the temperature with regard to the x, the distance traveled, which can also be written as the total heat flow divided by the cross-sectional area equals the same expression. This is a differential equation which is separable, so we can solve for dt and then integrate to arrive at an expression for t as a function of x. Well, first step is to actually integrate. Here, put down some integration marks. And then the expression will read minus pq over a lambda times x plus the integration constant c. As boundary condition, we had that the temperature at x equals half of the wire length. Remember, x is 0 was at the middle of the wire, and so x equals half the length is the end of the wire, and the temperature there was 273.15 kelvins. If we then solve for c, we end up with c equals 324.07 kelvins, and at x is 0 we are at the middle of the wire, so t center is t x is 0, and that's equal to the integration constant, so is equal to 324.07 kelvins. Thank you for your attention.